speaker is getting microphoned up, I would like to introduce Antonino Marasco, sorry. And you're going to be talking to us today about the gentle gas circulation of present-day star-forming galaxies. So again, I'll give you a 2-minute warning.
No, yeah, oops. All right, okay. So in the next, oops. Okay, so in the next 12 minutes or so, I'm trying to convince you that the processes of inflow and outflow that we observe in present-day star-forming galaxies are gentle, at least compared to expectation from theoretical models of galaxy evolution. I'm trying to divide, I don't have much time, but I'm trying to divide my talk in 2 parts. In the first part, I'm going to talk about starburst for galaxies, so low-mass galaxy, and the second part on normal Milky Way-like star-forming galaxies. So in the first part, most of the results that I'm going to show are taken from, let's see if I can find the pointer, yeah, from this study that is done in collaboration with people from the Arcetri Institute in Italy. And in this study, we are trying to quantify the warm ionized gas escaping from a sample of starburst dwarf galaxies in the local universe. The sample is called Duolin. You can see here the acronym, and you can see here Mr. Duolin. It's not my idea, but I found this to be a pretty clever joke. So this is a sample of 40 nearby starburst dwarf galaxies that comes from basically different catalogs, but all have this beautiful thing that they all come with ancillary Muse data. And so thanks to the ancillary Muse data that we re-reduce, although not for all the galaxies, but for half of the sample, so I'm going to show you results for 19 of these galaxies, we are able to study their kinematics and to quantify the mass outflow rates. These are starbursts in the sense that they all lie above the main sequence of star formation. Every time that you see a number is one of the galaxies that I study in my sample. There is actually a row of galaxies of very high mass that enter the sample, so this is not really in the dwarf regime. But most of the galaxies are in between 10 to the 7 and 10 to the 9 solar masses and are above the main sequence. So these are moment 1 maps, of the H alpha taken from the Muse data from the galaxies. And you can see here clearly, I think, 2 things. The first is that none of these objects can be classified as a regularly rotating disk. There are some signs of rotation. This one is a kind of nice rotating disk, maybe this one, but in most cases the velocity field is disturbed, and there are other cases where clearly there is no sign of regularly rotating disk. So I cannot tell you exactly what's going on in this galaxy in terms of what the gas is doing. But whatever the gas is doing it in a very gentle way, because if you see it, the color bar here, we are talking about motion between -25 and 25 kilometers per second. So these are numbers that are way below the escape speed, okay, from this galaxy disk. And if you look at the moment 2 map, so that quantify the velocity dispersion, this is the velocity dispersion where I already removed the instrumental broadening. So this is the intrinsic velocity dispersion. The number that you see are in between like 50, 70 kilometers per second. So larger than in typical star-forming galaxies, but not particularly large, again, compared to the escape speed. So I think that the first take-home message that we can say is that stellar feedback in these galaxies is shaking a lot their gas content, but it's not really producing a large-scale blowout. This is only, I'm showing you maps, so this is only qualitative, but let me move to a more quantitative measurement where I try to quantify mass outflow rates and mass loading factor. I have to define what is wind, so I'm opening here a Pandora box because everybody defines winds in a different way. But for me, wind is gas that moves at velocity comparable to or beyond the escape speed. So in order to assess what is the gas that is doing this job, basically I built very simple mass model for this galaxy that allow me to study the gas, the H alpha in the phase space. So I can trace this escape velocity line, and I put the H alpha in this phase space, and I can select the gas that moves at velocity beyond the escape speed. Now here the entire procedure is a bit convoluted, so you can ask me later the details if you want, but ideally we basically make 2 estimates, one that is very conservative, the other that is more generous, and we pick the average between the 2. Okay, and then I can use the formula that everybody's using to compute the mass outflow rates. There are actually many known unknowns in this formula. Someone mentioned already that there are, of course, major uncertainties on the electron density and the extinction. Those we can somewhat measure because we access all the lines of mu, so we can measure the electron density 10 to the sulfur ratio, for instance, and quite well for these galaxies. So let me put the galaxies in this plot. This is the, sorry, I use beta because for reason, but anyhow, this is the mass loading factor. So star formation rate divided by mass outflow, sorry, the opposite. Mass outflow rate divided by the star formation rate as a function of the stellar mass. You can see many points and lines. All the lines are theoretical expectation from different models of galaxy evolution, and the points are different observational probes. And you can see that there is a big scatter between the lines and the points. There are, in particular, there are measurements that are actually a higher redshift, where you expect these numbers to be much higher, and instead are pretty below. These are measurements by Alice Concas, who was supposed to be here actually, but couldn't make it. So where are the dwelling galaxies in this plot? Here, they align with this very low measurement. So we measure mass loading factors. Again, I repeat, these are valid for gas that move at velocity beyond the escape speed of a few percent, basically for almost all galaxies. So I think that there is no evidence for massive outflows, and most gas, even if it's shaken and is moved a bit, stays doomed to stay in the halo. And now we move to a different regime, Milky Way-like galaxies, but also to a different tracer, because we will be talking about H1 observation and comparison with models. So in this work that is still in preparation, we are focusing on a sample of 5 galaxies that are in nearby universe. They have mass comparable to those of the Milky Way, and they've been observed with very high sensitivity with Meerkat. Okay, 4 of these galaxies are part of this Mongoose survey, and other galaxies comes from another survey. All these galaxies are at 20 megaparsec distance, and this is convenient because it means that the field of view of Meerkat allows us to sample the entire virial region of the galaxy. So we can actually see if there are filamentary H1 that is coming in and can be and is dense enough to be seen. We can see it. The typical sensitivities are of the order of a few times 10 to the 18 centimeter square. So it's really very deep data, and the resolution is between 2 and 6 kiloparsec. We are going to compare the properties, the H1 properties of these galaxies, with those emerging from synthetic H1 observation of samples taken from 2 well-known simulation suits, the TNG50 suits and the FIRE2 suits. So these are 2 very different hydrodynamical simulations, both in the lambda CDM, but they differ from the codes used, subgrid recipe, resolution, many other things. So they really have, they allow us to sample the variety that we see in terms of prediction. So we are building synthetic H1 observation. We are really making mock H1 cubes with the same resolution, same pixel size. We add in the same noise, same smoothing, and so we are really trying to compare apples with apples. And also, this plot only shows that the galaxies are comparable in terms of their general property. The H1 content and the mass content of these galaxies is pretty much the same. So we are comparing apples with apples. Right, before I move to pretty pictures, because when you have simulation, you want to show pretty picture, let me show something more quantitative. There is already a difference if I look in between the simulated and the observed sample, if I look at the distribution of the H1 column density, so spaxel by spaxel, or the velocity dispersion. And in particular, you can see that the simulated galaxies show an excess of low column density gas and an excess of high velocity dispersion gas. Let me show now the pretty picture to quantify this in a bit more visual manner. So let me divide the sample in 2 subsamples. The first one, on the left, I will show you galaxies that are dominated by high column density H1. It means that the area covered by the galaxy is dominated by spaxel above 10 to the 20 centimeters square. And then on the right, the low column density dominated galaxy. So the area is dominated by lower column density material. If I split all the galaxies that I have observed and simulated, these are the moment zero map of these 2 subsamples. And you can see that on the left, I have the more regular galaxies that look like nice disk and nowhere things is occurring around them. And here, On the right, instead, you can see the more irregular galaxies. Now, all the Meerkat observed galaxies actually fall in this regular side, are all these 5 galaxies here. Okay, but the vast majority of the simulated galaxies, instead, is on the right side of this panel, where you can see clearly filaments connecting the galaxies with the rest of the halo. There are clumpy features around the galaxy, and even the outermost contour around the disk looks very, very irregular. This is something that does not happen in the observed galaxies and for some of the simulated galaxies. If I move to the velocity dispersion map, this is what I see. The Meerkat galaxies they show very flat and regular velocity dispersion profile with a peak in the center due to beam smearing. Okay, so this is an observational effect. And the simulated galaxies do not show that. So already in the regular one, but most in particular in the irregular part of the sample, I see multiple peaks in the velocity dispersion. Something is going on. What is going on? Let's try to understand what's going on. What is the origin of this difference? So this is the one of the take-home message from the second part, is that the H1 in simulated Milky Way-like galaxies is hotter and more irregular than in the observation. But let's quantify it. Let's try to understand why. Is it due to stellar feedback? Typically, feedback is not well constrained in simulation, and we know that it's quite powerful. So is it that the origin? So to inspect that, we look at correlation between the specific, the star formation rate surface density and the velocity dispersion. So in all this panel, you see histograms of the star formation rate surface density of all these simulated galaxies, spaxel by spaxel, in different beams of velocity dispersion of the H1. And when you move the higher and higher velocity dispersion beam, you see that in Fire 2 only, the peaks of star formation density move to the right. So there is, in fact, a correlation between high velocity dispersion gas locally and velocity dispersion, and star formation in Fire 2, but not in the other simulation, TNG, where the situation is more complicated. It's like multimodal. There is a peak here, but there is also this distribution here. What's going on in TNG? Well, we thought about the environment. Okay, can the environment be a bit more messy and complex with respect to the observation? So we did the analysis, and I have a plot to show you, but I believe, yes, I believe that since I have only 2 minutes, I'm going to move to pretty picture that demonstrate that what's going on is gas accretion onto the galaxy that is perhaps way out of control in this simulation. So this is one of the TNG 50 galaxy. This is the H1 map, but seen at a column density that cannot be observed, 10 to the 16 atoms per centimeter square. We cannot see that with Meerkat. But when you see at that column density level, at that sensitivity, you see that there are filaments connecting the galaxy with the circumgalactic medium, with the halo. And you can see here with these streamlines that are showing that this is actually low column density gas that is flowing in, not in a very gentle way, and feeding directly the high metallicity disk. Now let me move to the mock observation. So this is what Meerkat sees. Moment 0, moment 1, and moment 2 map. All the filaments are disappear, but there are some clumpy features that are basically the peak in the column density of the filaments that I show you. And you can see this bright spot here, here, and here in the moment 2 map. And these bright spots are spatially located in the region where the filaments encounter the disk. Okay, I think you can see it here very clearly. I think you can even see better if I smooth it a bit. This is the same observation at lower resolution. There are these bright spots. So I think this, I can show it more statistically, but this is the idea. So stellar feedback and gas accretion put together are a bit too vigorous in the simulation. Okay, and you can see it directly if you look at the morphology and the kinematics of the H1. I'm done. So these are basically the sub-conclusion of the tooth part, but the general conclusion is that gaseous inflows and outflows in the observed nearby universe are gentler compared to what predicted by evolutionary models. And that's it. Thank you very much.
Thank you very much. If the next speaker can come down and just make sure they're ready. Do we have any questions for Antonino? Yeah.
See.
Just making Monica do running.
Yeah, that's very good exercise, I think.
Thanks for the talk. So just a question. So if it's gentler, and what does this imply then for the simulations? Yes. So what is the effect? Is it that they have to tune down a little bit, like the effects of outflow and feedback and inflow, or is it dramatic?
I think that in the in every kind of evolutionary model, and in particular in the simulation, there is this sort of self-regulation, the feedback response to what comes in. And I believe, I'm not an expert here, but I believe that the culprit, the cause of this problematic is the fact that the simulation cannot resolve very well what comes in, because the mode the gas enters from the halo into the galaxy is based on so many physical ingredients that the simulation cannot really predict. But whatever is coming in, then the feedback must react. Okay, so it's not a matter of changing the feedback, it's a matter of resolving and better understanding the mode by which the gas is flowing in. And then the feedback will be adjusted in order to counterbalance that. And I believe that there is too much material coming in the sims, and then feedback is excessive because of it.
Okay, thank you.
Yeah.
Do we have any more questions? Yep, thank you. I'm sorry, it's the complete other side. It's all right, you're wearing your trainers today, it's fine. I'm just going to do it this way.
Thank you for that talk. In your studies, have you found any correlation between the gentleness of the inflows and outflows and the strengths or the presence of the bar in the galaxy? For example, would a strong bar lead to a gentler inflow because it's so collimated?
No, we didn't look into that. Of course, in the dwarf sample, there is nothing of a sort. These are all irregular, but we didn't look in the Milky Way. It would be nice to see it. Yes.
Thank you.
I am going to very quickly invoke chair's privilege and ask, did you look at different redshifts? And how can we look at this at different redshifts? What would we expect?
No, because we really wanted to, in the last part, we really wanted to focus on H1, so you are doomed to look at very nearby universe. And for the other side, no, because we wanted to focus on the dwarf galaxy population that is supposed to be the one where feedback according to model is the most ejective, because there is a big mismatch between the content of baryons that are supposed to be in there and what's actually in there. And so because of that, we will be focusing on the nearby universe again. So because of this, we decided to focus on nearby galaxies. Yeah.
Right. If we can thank Antonino again.